afternoon, everyone. Filipe, I saw you for a second. You disappeared.
I'm here again.
Yes. Okay. Okay. Please.
Okay. Good afternoon to all. I'd like to thank everyone for attending another START project webinar and for your interest in following the activities we are carrying out in the START project. So, as you know, this webinar session is focused on the use of powder technology to produce tetrahedrite-based materials. And the presentation today will be made by three members of three of the consortium partners. So, Bruno, do you want to introduce the speakers?
Yes. First of all, I would like to thank everyone again on my behalf for me. And then I would like also to say that I'm particularly proud that we are talking about powder metallurgy here because we are from the Powder Metallurgy Association, EPMA, and so this is really our business every day. The speakers today are from three of the partners of the consortium, and in particular, we will have from MBN Nanomaterialia, Italy, Serena Busatto, who will be the first speaker, followed by from Poland, from GeniCore, Damian Karpowicz, who will be the second speaker. And finally, last but not least, from Sintef, Norway, we will have Patricia Almeida Carvalho from a research center that will explain about the measurements done on the materials that have been produced with the powders made by MBN and by the technology developed by GeniCore. So I see people are still coming in. Of course, everyone will join in a minute or so, but I think we can probably start. Serena, if you can come on stage and prepare sharing and prepare starting your presentation. There's Serena.
Hi. Good afternoon to everybody. I will
Good afternoon. Yes.
share my presentation.
While you share, I will also add that we are recording the webinar, so not today, but later in some days, you will also see all this on YouTube, on our YouTube channel. So please follow our website and social media, and you will be able to review all the webinar for yourself later. So I see Serena is ready. So the virtual floor is yours.
Thank you, Bruno. Thank you very much. So today I will be speaking about the mechano-chemical synthesis of thermoelectrically optimized tetrahedrites from mine tailing. So first, I would like to briefly introduce you to the company, MBN Nanomaterialia I work in. So this is a small company based in Treviso, which is in the Venetian area in the north of Italy. And we work on nanostructured powder materials, metal alloys, and special alloys with superior physical and mechanical properties. And we are expert also in for a variety of application, and we work also a lot on research and development. I don't know if you can see the next slide because it's kind of slow. Okay, yeah. So MBN uses a proprietary high energy ball milling technology, and the powders produced in this way show fine and homogeneous distribution of the element. The powder particles are micron-sized, but they have ultra-fine nanocrystalline structure, which confers superior properties, mechanical and other properties. So compared to other ball milling processes, the Mechano-made delivers very high specific impact energy with high velocity and control impact of the milling means. And this allows to produce nanophase powder materials with the continuous welding and the fragmentation and the fracturing of the powders. And the prolonged milling treatment promotes alloying effects at the atomic level, and also the formation of solid solution, intermetallics, and inclusions. This is a brief showcase of the portfolio of special materials developed by MBN. We have we produce a variety of metal alloys, oxide dispersion strengthened alloys, intermetallic cermets, metal matrix composites. And all the powders are engineered to be treated by specific downstream manufacturing processes. For example, powder consolidation by SBS sintering, powder extrusion, thermal spraying, additive manufacturing technology. And this is some examples of the uses of the materials we produce. And it's very important to know that, so sometimes, most of the times, first we think of the uses of the materials and the manufacturing processes they will be subject to. And then we think of how to engineer the powder. So one of the examples the example I will be talking about today is of the thermoelectric materials we are producing for the START project. Okay. Yes. So thermoelectric materials allow for the direct conversion between heat and electricity. Thermoelectric devices are built up by putting together multiple PN junctions that are wired electrically in series and thermally in parallel to make up these very extended devices. They have several benefits. So, for example, they are all solid state, they have no moving parts, they emit no noises and no emissions. Their characteristics are evaluated, the performances of these materials are evaluated by the figure of merit ZT, which is here you can see how the formula describes it. And sorry. Okay, so all this sounds really nice, but in fact, there are some challenges in the industrial broad exploitation of thermoelectric materials. Their efficiency is still too low, and the efficiency is directly correlated with ZT. So here you can see how the efficiency changes with different values of ZT. And also they rely, most of the most efficient thermoelectric materials rely on rare critical or toxic elements. And also they are rare and they have problems of availability of the raw materials. So for these reasons, they are still limited to niche applications in most cases, but there are a lot of possible other applications that have been demonstrated and would be really important to apply and would be convenient cost-wise and efficiency-wise if the ZT values would be a little bit higher. Okay, so in this presentation, I will actually talk about why mechanical alloying is very important for thermoelectric materials and can provide thermoelectric materials with, can increase the properties of thermoelectric materials. So first of all, I will talk about the industrial scalability of the process and the fact that it's compatible with downstream consolidation techniques such as SPS. Then I will talk about the fact that mechanical alloying provides a material with nanostructure, which is very important to decrease thermal conductivity, which increases ZT of the material. And also mechanical alloying is a low temperature process which allows to process materials and phases that are not stable up to their melting point, which is the case of tetrahedrites that we use as our raw materials. And finally, mechanical alloying is a solid state process that doesn't have byproducts. So it is possible to modify the material composition of the raw materials. Mechanochemistry is, as I said right now, a solid state synthesis route. So this is a green process and it is easily scalable. It depends, there is a large parameter, space parameter that can be adjusted. And the reactivity of the powder particles is promoted through mechanical forces under non-equilibrium conditions near room temperature by the transfer of mechanical energy to the particles, which generates dislocations and other defects, enhances the mass transport properties and the rates of particle-to-particle collisions, therefore also exposing continuously new surfaces, and all of these promotes reactivity. Here I showed some examples of mills that are used at lab scale, but what we actually use at MBN are much larger high energy ball mills. Here you can see a person for scale, and we produce very large volumes of powders. And so the high productivity that we can reach combined with the sintering technology that is developed at GeniCore and will be described later by the next speaker, permits to make this process industrially convenient. Let's go then now to the nanostructure and why this is important. And I will first show you the figure of merits of thermoelectrics, how thermoelectric works. So here is an example of a thermoelectric junction. And what happens in thermoelectrics is that there is the carriers that are electrons in N-type materials and holes in P-type drift from the hot surface to the cold surface, and this builds an electrical potential across the material, which eventually counterbalances the drift. And the proportionality constant that of the created potential over the temperature gradient is called the Seebeck coefficient, and describes the thermal power of the material. Then this is the thermoelectric figure of merit, ZT, and depends on several properties. So the Seebeck coefficient is S, and then we have the electrical conductivity and the thermal conductivity. And as you can see here, unfortunately, the Seebeck coefficient and the electrical conductivity have two different trends. So one is higher for insulators, and the other one is higher for metals. So while the thermal conductivity increases with free carrier concentration. This is why the requirements for having high ZT are to have a high thermal power to produce a sizable thermoelectric effect, but also to have a high conductivity to avoid Joule effect, and also to lower the thermal conductivity, as you can see from the formula here, to maintain a large thermal gradient across the device. So basically what we need to find are the so-called phonon glasses electron crystals, so thermal insulators but electrical conductors, which in fact are found in heavily doped semiconductors. But why nanostructuring is so important? It's so important because the thermal conductivity has two contributions. One is from the lattice and one is from the electrons. But the one from the electrons is related to the conductivity by the electronic conductivity by the Franz-Wiedemann law, and therefore it cannot be lowered. So what we need to minimize is the lattice contribution. And we can do so by nanostructuring because the grain boundaries act as phonon scattering size, and minimizing the mean free path of heat carrying photons can minimize thermal conductivity, while the electron transfer is almost not affected by this. Let's proceed then to talk about the tetrahedrites and how these materials can be treated by mechanical alloying or mechanochemistry. So tetrahedrites are sulfur salt minerals that are very common and are one of the main source of copper and silver worldwide. They are abundant in nature and are found in mine tailings, copper abandoned mines normally. So they have many positive aspects in terms of they have no critical toxic or element and are suitable for large-scale production, and also have very tunable compositions that confer them diverse properties. Unfortunately, the ZT values are not so high compared to other materials, but their cost and availability make them still very, very important. So here I am showing a map of Europe with the mineral, the mine sites that have been identified by our partners in as sources of tetrahedrites. And these are all our partners that are providing us with mineral concentrates from all around Europe and also from Colombia. This is an example of one of the mines. It's in Slovakia, and it's called Striborna mine because here the tetrahedrites are also rich in silver. Okay, but how about the mineral tetrahedrites can have these very variable compositions. So they are normally present as a solid solution between the tennantite and the tetrahedrite form. So this means that at the antimony site, both antimony and arsenic can be present, and also that the copper can be partially substituted with other transition metals. Iron, zinc, manganese, and mercury are some of the most present in mineral tetrahedrites. Fortunately, the thermoelectric properties are not sensitive to the ratio arsenic to antimony, so this is a good thing. But there are some drawbacks. The fact that different ores from different mines have many different chemical compositions, so it's difficult to find a process that works for all of them. And also they contain variable amount of secondary mineral phases that can be difficult to treat, like chalcopyrite, quartz, and pyrite. This is the crystal structure of tetrahedrite. It's a very complex unit cell. It's composed of 58 atoms per unit cell, and this is one of the reasons why the thermal conductivity of this mineral is so low. And the other reason why it's so low is because there is a rattling motion of some copper atoms that are resembling those of some other thermoelectric material like scutterdits and clathrates that also contribute to giving strong phonon-phonon scattering and to lowering the thermal conductivity. Here is here you can see how all these different metals can be incorporated into the tetrahedral sites, the copper sites. So yeah, there are two different copper sites, tetrahedral and trigonal copper sites, and 2 out of the 6 tetrahedral copper sites can be substituted by other transition metals, conferring them with higher electrical conductivity and higher Seebeck coefficient. Here is for some further reading. This is a very recent paper and explains better why this rattling motion, and it's even more than a rattling motion of the copper atoms, can provide this very low thermal conductivity. The synthesis methods for tetrahedrites are multiple, some of them can be scale up and some other no. So melt crystallization and solutions phase synthesis give very good phase control, but unfortunately are not scalable. In addition, solution phase synthesis also gives the nanostructure to the material, but this is accompanied with byproducts. Uh, so other methods that have been tried are reactive SPS, which is very promising, but for now the phase control is not that good. And finally, mechanical alloying, followed by spark plasma sintering, is one of the best methods for the synthesis of tetrahedrites because for the low temperature, medium time, good phase control, high scalability, and also nanostructuring and easy incorporation of the mineral concentrate. And then the rapid plasma sintering process mitigates the grain coarsening. That's very useful for preserving the nanocrystalline structure. Okay, so then we go to, in this part, when I will explain you how practically in the START project we use mechanical alloying and tetrahedrites. So we performed a very extensive experimental campaign using ball milling at lab scale, sintering, and measurement of the thermoelectric properties to identify the most performing tetrahedrite composition in terms of transition metal dopants at the substitutes at the copper sites. Taking into consideration many factors, among them the doping elements already present in the mineral concentrates, the phase formations, the thermal properties, electrical properties, and the stability of the tetrahedrite phase with these substituents. So we work in these quaternary space diagrams and we identify the most performing composition. With this, we try to replicate at a larger scale. So here at MBN, with our high energy ball mills, the synthesis, and we could obtain the same phases that were obtained at lab scale. Also, we noticed that the presence of transition metal substituents not only improves the figure of merit, but also favors the stabilization of the tetrahedrite phase over the concurrent famatinite, which is not thermoelectric active. Okay, here I will show you how we balance the composition of the minerals. So in green, you can see the composition of one of the mineral concentrate we received, and it was measured by electron microprobe analysis. And in blue, it's the target composition. So we identify what is the limiting element present, which is normally iron. So, and this sets an upper limit to the amount of mineral that we can include in our tetrahedrite if we want to reach the target composition that we selected. So then in this case, it was 40%. So the rest needs to be balanced by adding synthetic elements. Of course, we count copper together with, silver together with copper. And in case there are arsenic or bismuth in the composition, we count them together with antimony because we know that they will substitute that site. Okay, then we compensate with synthetic elements to reach the target composition. So this is what we tried. This is an example of a concentrate that we received that was crushed and homogenized tetrahedrites, but unfortunately contained also some amounts of other phases such as pyrite and quartz, which were quite stable also to the ball milling process, which in fact was not effective in the decomposition of these secondary phases. But fortunately, there is something that we can do, and here I use the started robot to show you the electromagnetic separation that is very interesting process, and it's used, yeah, it's largely used in the mining technology because it permits to separate magnetic and non-magnetic materials. And in our case, it could completely remove pyrite and quartz, like almost completely, so that we could get a concentrate that was more or less free of these other phases, difficult to treat. And in the end, what we did was to mill together. So as I showed you before, part of mineral concentrate crushed, homogenized, and treated by electromagnetic separation, balancing the composition with synthetic powders, and then like okay, ball milled, sinter the material, and then we measured the thermoelectric properties, and we found that the ZT values of these concentrate of these samples containing mineral and synthetic elements are yeah, good compare like good also compared to purely synthetic tetrahedrite examples reported in the literature. Okay, yeah, they are here. You can see them in this region of the graph. So for now, it's not a bad result. So what I showed you in this presentation was the fact that we could identify. We first identified the element substitution that would give the best thermoelectric performance. We optimized first the composition for the synthetic tetrahedrites. Then we developed a scalable and environmental friendly synthesis, powder-based synthesis method for producing a large scale of mineral-derived sulfide P-type thermoelectric materials. And we also optimized, not we, but GeniCore optimized the SPS consolidation of these materials for the production of mineral-derived sulfide P-type thermoelectric legs. Okay. And for now, our results are here in the middle of the graph. But as I told you before, even if we are not having ZT that are very high compared to these materials, in our materials we don't have rare, toxic, or costly element, and so this is an industrially valuable route for thermoelectrics. Of course, this is not, it's just a small part of the production process of a thermoelectric device. So what I explained today was only the development of the P-type leg. So in other webinars, we will also talk about the development of the N-type material and also all the other, oh wait, sorry, and also all the other things that are necessary in order to have good junctions to protect from the oxidation, to minimize the mismatch in the thermal expansion coefficient, and all the others things that need to be optimized in order to have good thermoelectric junctions. Okay, and this I would like to yeah, wish you all a happy P-Day. And if you have any question, you can type them in the box below and I will be happy to take them. Thank you.
Thank you, Serena. Thanks for the presentation and also for being really timely. I think we are even in advance in case. I don't see questions in the chat, but I will open the discussion anyway. So anyone who wants to open the microphone and pose a question now should be able to do it. So please don't be shy. Let's see if there are questions for you. Anyone? Yes, Siddharth? Can you try to speak? Hello? We see you on stage, but can you speak? Otherwise, if you can post the question in the chat, we will reply. Or then I see Giovanni also. Maybe Giovanni is able to speak. Let's see. No, let's see. Maybe I can do something for you. Can you try now, Giovanni? Hello? Is anyone able to speak? I mean, questions are there, but
Yeah.
they don't come through. Genevieve, maybe you
Yeah,
can.
Bruno, can you hear
Yeah.
me?
Hello. Yes.
Yeah, I
Finally,
think
someone.
I don't have question for Susanna, but I think I can advise my colleagues. You must accept the activation of the camera and the microphone. If you
Oh,
don't,
yes.
you're not able to speak online.
Yeah, that might be the problem. Yeah, I can request maybe, but doesn't seem to work. If you write down the questions, maybe we will reply to
Now,
them.
in the meantime, Susanna, what timeline do you think is possible to obtain, a small module that works? Huh? I mean, with a functioning P, with a functioning N, and a working temperature which provides some reasonable power. What
Yes.
time?
So sorry, you were still talking? No.
It's fine.
You hear me?
Yeah, I think I can. I think that within like the next few months, because now at the moment we have developed also the N-type
Mhm.
material, which is not based on tetrahedrites, because unfortunately tetrahedrites can only be made P-type and be efficient. And so now we sintered a lot of pellets of both types, and we are like on the way of making our first device. So I think it's just a matter of few months.
Okay, thank you.
You're welcome.
Let's see if someone else can speak. Marcio, did you manage to talk? Maybe I see you also on stage. Your microphone should be open. Ah, apparently not. Then please type your questions in the chat, really, and if not now, maybe Serena can reply to you in
At the
separate.
end of the session, or
At the
yeah,
end of the session, maybe, yes. Yes, if we have some time, yes, of course. Apparently, there is some problem with the microphones, but Genevieve demonstrated it's possible, so there
yeah.
must be something not working. There is a question from Victor. I read it. How important is the crystallization and purity of the tetrahedrite? Because impurities always occur in tetrahedrites.
Yeah, it's true. Yeah, we noticed, especially yeah, in the mineral concentrates, we always see some presence of secondary phases, which can like almost completely, like not completely, to a good extent, be removed by the electromagnetic separation that our partners have. But yeah, there remain some issues with especially quartz but in the end, if they can be milled quite a lot and turned into nano inclusions that provide more scattering centers for the phonons, I don't think that this could be just a bad that have just a bad contribution. If they are present in small amounts, yeah, they shouldn't affect too much the properties.
I see also Anna Luisa. Can you speak? Do you manage? Maybe not. Right. Okay. So it seems we have some problems with the questions, but let's hope for the next
Yeah.
speaker we can have some.
Anyways, I will be here later, so
Yeah. Fine. Okay. So please type your question in the chat, and Serena will take them later. Thank you.
thank you, Bruno.
Thank you, Serena. I think we can move now to the next speaker, and that is Damian Karpowicz, that I call on stage for the next presentation. Here is Damian. Yes, you're sharing already. Thank you.
Good afternoon, everyone. So first of all, I would like to thank you for joining us in the webinar today. I hope you will find the shared information interesting. So I am the Damian Karpowicz, as introduced. I'm representing GeniCore company, and for today, I would like to show you something more about the devices, because as you heard, the SPS technology is used in START project. So I would like to share with you what kind of devices can be used, and also some examples of applications to give you a spark maybe for new ideas, not specifically maybe related with what we are doing in a START project. So with regard to GeniCore company, the general informations, the company was founded in 2012. It is based in Warsaw, Poland. We mainly focus on SPS technology, so everything what is related with SPS technology is in our interest. We are the SPS device manufacturer, so this is our core business. But also we are producing the DEC material with technology which has been already mentioned, the PPC technology, so the pulse plasma compaction technology. I will show you there in the next slides what is the difference. We are also supporting SPS users in every aspect of SPS technology. So in general, we can say that if you have any kind of questions or needs related with SPS technology, please always feel free to contact us directly by using emails provided on our website. So we are also the part of MS Galleon Group. It needs to be emphasized because it merged more than 30 companies and have more than 30 years it is more than 30 years on the market. So this also allows us to reach different applications in a fast way. So let's go to the SPS technology itself, because I assume it will be good to remind us the basics, and maybe for someone this is something totally new. So the general principle is that we are mixing the powder, and we are using the metallic powder and graphite molds to generate the fully dense samples by using the pressure and DC current in pulse form. So the basic difference in sintering by using other methods is that in the case of UFAS technology, so SPS technology, we are using the Joule heating, which generates the heat inside the powder. So as we can imagine that when we are generating the heat directly inside the powder, the efficiency of heating is way higher than in conventional methods where we heat by radiation, like for example in hot pressing, where we need to use different kinds of radiators to generate heat and then to heat up the powder. The second thing, besides the rapid cost-effective process caused by Joule heating, is low energy consumption, which is also the fact because the process is very, very fast. And thanks to the sintering technology, which utilizes pulsing, we are able also to achieve lower sintering temperature for the materials. I will show you the examples in next slides. When it comes for the pulsing system, when you will read some information about the SPS technology, you will find that there is no there's no 100% fact how the pulsing works. So there is also people using SPS technology which state that pulsing is not important and it is not necessary. Of course, we need to say that for some of the materials it's truth, but there are materials where the pulsing have a big impact. So today I will try to show you some examples of those kinds of materials. When it comes for GeniCore, maybe this is not the perfectly colorful graphics, but however, this is the waveform just took out from the oscilloscope to show you the waveform of the pulse of the example of the pulse. In case of GeniCore, it is we can generate pulses below 1 milliseconds, which we like to call the micropulsing. For the SPS process, we are also using the graphite molds can be used. Also, different kinds of mold can be used, but in general, the graphite molds are the best one to be used, thanks to the high resistance for pressure and for the temperature. And in GeniCore, we are able to produce the molds for our customers by using just the graphite blocks. Otherwise, you may find that purchasing the graphite mold may be expensive. So it is good to have for example, like in our case, the graphite CNC dry cutting machine, where we are able to produce the molds with very high accuracy, which you can see on the right side of the slides. Because this is the graphite without any covers, without nothing, just a graphite, but cut it out so accurately that it can shine. So for the production process, as you can see here on the left side, we can see the pre-compressed samples. However, it needs to be emphasized that in SPS technology, we can directly sinter the powder. In this case, I just wanted to show you that for some cases when we produce, like for example, in multi-cavity, multi-layer forms, it will be easier for the operator to just load the molds with this kind of pre-compressed powder rather than just to pour the pure metallic powder. We also use the graphite foil, which allows us to separate the sample from the graphite mold, which increase its lifetime significantly. So we can assume that more than 100 processes can withstand, one mold can withstand more than 100 processes if designed correctly. So UFast and SPS technology is not only the production of the single samples, which is often misunderstood. We are able to design and produce molds, which allows us, like in this example, to produce 65 pieces of RNGN cutting insert, which is used for Inconel machining. It, of course, takes some time to do so. However, if this kind of process is developed, it is very, very energy efficient, and it allows to produce a lot of samples. So when it comes for the temperature measurement, so how we control what is happening inside, I think it is worth to consider that temperature control is very, very important in SPS technology, because we need to watch out to not go too much with the temperature. And after people see by using even other devices that parameters are not so maybe accurate. But in this case, in GeniCore solution, we are using mostly the pyrometers. And when we make a precise and accurate measurements with the thermocouples first, then the customer or user can just use the pyrometers. So in this case, we are using the axial parameter, which is in the top stamp, top electrode of the device, and also two side parameters, which combined allow us to cover the full range of temperature, so starting from room temperature up to 2500 Celsius degrees. It needs to be mentioned that in this specific example, we intentionally do not show the graphite blankets to allow you to see the laser dot, which typically in SPS devices helps you to position the parameters correctly by automatically control it with the servo mechanism and PLC. So going to the devices, the smallest one, UFast Compact. It is very powerful, yet quite small. The interesting fact is, which we like to mention, that it can be transported even with a typical elevator, which we did in the recent event. We also posted it on LinkedIn because it's very comfortable to have this kind of size. And yet, as you can see here, a very, very powerful tool when it comes for the sintering. So the 3 kiloamps is enough for us to sinter 40 millimeters tungsten carbide, as you can see here, and even with very high heating rates, which is 100 Celsius degrees per minute. And of course, we achieved the full density. So we can sum this up that this small device is all what is necessary for R&D institutes to work on the bigger, to work on the small samples to hopefully scale it up in future. So Here we can also see that the UFAS compact have several types, models. So basically this is the information which you can find on our website, but I wanted just to show you that there's several types of the devices. So we try to be as flexible as possible when it comes for R&D centers, because not always the sample need to have 40 millimeters. Sometimes 10 millimeters is all what we need to have. And you can pay attention that in the most advanced version, we also add induction heating. Of course, for such a diameter, it is not necessary, but in case if scientists would like to see the impact of induction heating on the tested samples, so we give this opportunity in the UFAS 40 Pro. UFAS GC device is the middle-sized device, single chamber device, which allows us to produce samples up to 100 millimeters. It needs to be emphasized that up to 100 millimeters means the full density, best quality sample which can be produced by using SPS technology. Sometimes, of course, you will be able to produce bigger samples, but 100 millimeters is what we recommend for this pressure and current available. Again, several types of device is able to be produced. It needs to be emphasized that in this case, the device is fully modular, which means that we can start with UFAS GC35, in example, and then in future upgrade it easily up to UFAS GC85. And this is basically because the power supply is modular, so every time when we would like to increase the power, the power or the current to be more specific, we just add additional module. And when it comes for the high vacuum, as you can see, it is also available. So every type of the device which can be purchased have a space and wiring which allow us to add the turbomolecular pump in the future. So in general, it allows a lot of companies to start even with limited budget, and then if necessary, upgrade the device. The UFAS hybrid, so the biggest device which is possible when it comes for GeniCore, very big diameters, which requires more than just the DC power supplies to offer the uniform temperature distribution when having at the same time the high heating rates. So as you can see here, there are several types. So currently we are building the biggest one at GeniCore, which will have more or less a max heating power of 1 megawatt when it comes for the DC power supply. So as we can see, very powerful power supply that allows us to use a lot of DC heating and max heating power for induction. So separate AC power supply to somehow enhance our sintering. So we should understand that, like, when we would like to sinter a very big diameters like 20 millimeters, 200 millimeters, 300 millimeters, we should also consider the volume of the sample. So if we would like to heat in a, let's say, SPS way, so with high heating rates, with limited grain growth, which is the main cause of very good quality of the samples, we need to do it in a proper way. So that is why we allow our customers to use the DC and AC power supplies independently. And thus, the induction plus the DC power supply allow us to achieve very high heating rates, yet very good uniform temperature distribution. So this is the main idea for UFAS hybrid. And as you can see here, I like this picture because our colleague here on the left side try to not smile, but it is hard not to smile because, to be honest, all of our team is quite excited that we will probably finish this device in this year, which probably opens a new window for new applications where SPS technology were not yet be considered. So hopefully we'll have something to share with you again by the end of the year. Also, it was mentioned that the technology is scalable. Of course, it is. We just saw the example for the size, and here I'm presenting you the example for the production volumes, meaning of very, very high production samples in a way that we are able to produce maybe smaller samples but faster. So the idea was to generate, to construct, to build the device and spread the sintering process in the three stages, which is the first stage is on the left side, the chamber on the left side, degazing, then sintering and cooling. So the idea was to allow the operator to just start the shift, come to the device, load the molds, and then forget anything is happening with it. So it is fully automated process, which also use mold transportation in during the high vacuum state. So at the end of the shift, we are able to take out the molds from our device. In this specific case, this device was produced for GeniCore to allow us to enhance the production of DFC material, and it allows us to contain up to 6 molds in the chamber, in the last chamber. The pulse plasma compaction technology is the one which we use for the DEC material production, so diamond enhanced cemented carbide, and it was also mentioned in the previous presentation. So to give you just some feelings about this technology, it is very similar to the SPS technology. However, we are using 2000 volts instead of 10 volts. So here we can confidently say that we have plasma inside. So it allows us to generate the rectangular high voltage pulses and to sinter, in example, tungsten carbide with 30% of diamond content in whole volume without diamond graphitization. So this is the technology which we can say was the first one from which we just upgraded and built more devices like UFast. And going to the DEC, as you can see here, tungsten carbide matrix with diamond content, just to make you understand what kind of material we are talking about. And from there, we are going to the applications. So to give you just some examples where the SPS technology can be used effectively and why. So super enhanced ceramic whiskers. The cutting inserts using for inconel machining, which I mentioned before. Here we can see the table to show you the difference when it was hot pressed. So this is the conventional method which was previously used. And then when we used a UFast technology to sinter the same cutting inserts. In hot press, it was a very big piece of the material, and then they laser cutted it. However, in US, the energy costs increased a lot recent years, so customer asked us if we can check if UFast can produce it more effectively, which we did. But in the meantime, as you can see here, we saw that by utilizing UFast technology, we are able to achieve better quality, like in this example, fracture toughness plus 20%. And when we can see the production examples, which is a real readings from the power supply, we can see that UFast mass can produce almost 500,000 pieces per year, just with one operator and with very limited energy used. And as mentioned before, 65 pieces per one run. So it needs to be emphasized that we are able to achieve better results when it comes for mold designing. And this is just a picture to show you the final product. Of course, to achieve such a shiny effect, let's say, for the cutting insert, it is also machined after the process. Nevertheless, we produce it in near net shape, which limits the machining to the very minimum. When it comes for the comparison also the UFast technology to conventional method, I mentioned the limited grain growth and the lower temperature of sintering. So this is specifically what you can see here. The SEC material sintered with 1950 Celsius degree compared to conventional method 2150. The hardness of the material achieved by UFast was higher. Also, the sintering process time, you can pay attention to it, 75 75 minutes compared to 270. And this is literally because we are heating directly the powder. The cooling time, unfortunately, we didn't have a comparison to the conventional method. Nevertheless, I think we can easily assume it was also shorter because we use advanced cooling system for the stamps, and the pore size, crystal size also smaller. When it comes for the limiting the grain growth, I think this alumina can be a great example because with the naked eye we can see the difference in conventional method on the left side and with UFAS technology on the right side. So this is the phenomena which can increase the quality of our materials. Transparent ceramic, there's a lot of applications where it can be used. We specifically had a chance to produce the covers for the missiles. So infrared and guided missiles need to have covers on the top. So basically, transparent ceramic can be used there. However, there are some challenges related with the shapes when it comes for this application. Nevertheless, the idea was to show that you can produce with SPS technology uh, fully transparent ceramic with commercially available powders without any additives. So no lithium, nothing, just the commercially purchased powder. And with one processing step, we are able to achieve the transparent ceramic. Also, magnesium aluminate spinel can generate a very interesting results. If you would like to know more about it, please feel free to contact me and I will share the details with you. Another example which I would like to share with you is a tungsten carbide. This is specifically a project where we worked for our customer in China, the second biggest tungsten carbide producer, and they asked us to provide a device which will allow them to produce tungsten carbide with very high density and hardness and 60 millimeters in diameter, 30 millimeters in height. So quite big, quite big volume, almost 1.5 kilogram of tungsten carbide, and we achieve it. We provided both the device and the sintering process technology to allow them just start the production immediately after commissioning. And as you can see, the mean value of HV10 was 2,515, which is kind of quite good results in their opinion. And no porosity at all. So as we can see, the good sides of SPS technology is visible here. For diamond enhanced cemented carbide, so the material produced with the pulse plasma compaction technology, it was quite hard for us to start selling this material because besides selling the devices, we are also producing DC material, as probably mentioned before. So people initially didn't believe that we can sinter tungsten carbide with diamond in full volume without diamond graphitization. So we needed to generate some examples, and here you can see the one. So we purchased the drill just in the market and replaced the tip with the DEC material. And with the help of one of the company from the group, we just made a drill. And after that, we performed the test. So dry drilling test with the reference drill and the DEC drill. So the first and the second graph is for the DEC. So it means we made a hole and the drill was ready for use again. And for the reference drill, we can see after 8 millimeters, it was burned. Probably it is caused by the diamond good thermal conduction. However, this don't need to be understood. We just see with the naked eye that this material works good. In case of mining, we also have a lot of applications, but I will today show you the one from which it was started. So rotary pivot knives, similar situation. We just took out the tungsten carbide and put our DEC material in it, and you can see the difference. So the tools after performing a test with the mill, as you can see here. So we can see that DEC material can withstand much more than just typical tungsten carbide. functionally graded materials, we needed to learn how to sinter different kinds of material in layers. In this case, a layer composed of DEC, 30% of diamonds once formed on tungsten carbide substrate, to just limit the cost and make the brazing easier, because brazing is hard for DEC material. We need to admit that. It took us some time to understand how to do it. Near-net shape production, this is more related with the disadvantages, which we can say, for SPS technology, so limited geometry. However, as you can see, we can produce also near-net shape materials. This is the button bits, which are used in mines for drilling in a roofs, an example, and also functionally graded materials, so DNC either on the top and tungsten carbide on the bottom. There are also more sophisticated shapes available, even 3D printed by new methods. However, it will take some time to show you the results. So thank you very much for your attention. I hope you like it, and if you have questions, please feel free to share.
Thank you, Damian. I think you also have been quite timely, so we are ready for questions. I will try again to open the discussion. Let's see if someone is able to speak. Maybe I can start, Damian, with just a question. If you could maybe comment on the process used for tetrahedrites briefly, maybe if you can give some information as well on that.
When it comes for that, I'm not directly involved in the project. However, I know that the GC type device was tested, and then the pulse plasma compaction. So the result is very, very promising. We didn't face any problems, as far as I know, at least when it comes for the sintering. So for sure, we can say that it will be scalable. We are able to scale it up with the mass device currently, which is operational at GeniCore. But also when it comes for the size, I believe it will be possible too by utilizing hybrid.
Thank you. Patricia, you're on screen for your next presentation, or you have a question for Damian?
No, I'm
She's ready. Okay. Any more questions? Is there anyone who wanted to ask about the technology for consolidation? I don't see questions in the chat. Is anyone able to open the mic and speak directly? You should be able to do it. Neves was able to do it before. No, I don't see people coming up. So I think, again, if there are other questions, we can even address them at the end if you want. Thanks again, Damian.
Thank you very much.
And you can always get in contact with them anytime, I think. So Patricia is already here. As I was saying, she is the next speaker. You anticipated by sharing. Now I have to find a way to get back to the previous way of there's a question, but Damian is already going, has already gone. Unless he wants to come back briefly, Damian. There is a question from Alvisa. Damian, can you come on stage just for replying to Alvisa, or we do it at the end? Okay, let's do it at the end. But I have to go back to the previous view. Just a second. Yes. Okay. So Patricia is here. She already placed her slide on the screen. So she will talk about assessment of our materials. Patricia, the floor is yours.
Thank you,
See you
Bruno.
in 30 minutes.
I'm glad that I could show the slides, because I have to show them in PDF, because I have a Mac and somehow it's not cooperating with this platform.
Yeah, it's not compatible.
But,
okay, but it works.
Okay. Thank
Yes.
you, Bruno.
See you later.
thank you so much for attending, everybody. I hope we'll be able to show you nice things. So I'll be showing you some results of the project, of the START project. And I will also try at the same time somehow showcase some of the possibilities we have at Sintef. So one of the goals of Sintef in this project, and I have to change the slide like this, is characterization. But before I'm going to, it's essentially characterization, but I'm going to also show you some, just give you an idea of what Sintef is. I don't know if you know, but I didn't know before I came to Norway. I'm originally from Portugal, but now I'm living here for 10 years already, working in this institution. So this is a research institution. It's very large. We are about 2,000 people, of which 1,500 are researchers. It has two main poles, one in Trondheim and one in Oslo. I'm situated in Oslo. And they always like our marketing and this type of people at institutions. They always make these very beautiful slides where you see the nice mountains in Norway full of snow. But basically what they want to show here is that we are involved in most activities. So ranging from wind, solar, oil, boats, construction, all sorts of things. And so here you have just a list of the things we do. We work in our group, we work mostly with characterization of materials. We try to use advanced tools. We also do a lot of modeling, mostly modeling in atomistic, so DFT type of modeling. So in the project START, as I told you, our major role is characterization. We are also involved in other work packages, but it's mostly characterization. So basically what we do is we get materials from the other work packages and then we provide information back. We also do some processing, but it's more, it's not so industrial applied, so it's more fundamental type of processing. So as Serena already told you, we are dealing with tetrahedrite. And so tetrahedrite is based on copper, and these copper atoms have two types of positions, one in which it has an oxidation state of 1 and another one in which has an oxidation state of 2. So it means that we can replace these atoms with elements which have similar, which have the same oxidation states. And so what we have tried to do when we started was to try to see how could we maximize the performance of the thermoelectric materials. And so if we go to the literature, we see a lot of different types of elements tested. And we decided, okay, let's try and see what we can get with these elements too. Of course, for the antimony, we don't really want to replace it with arsenic or tellurium, which is, they are not very nice, and tellurium is not very abundant. So we stick with antimony. So one of the first experiments we did, we decided to use a design of experiments. This matrix is, we decided to use the Taguchi method, but we were a bit too wild, so we decided to go to very high variations in composition, which in the end revealed to be not the good choice. And at the lab, we also did, in addition to what Serena is doing at an industrial scale, we also use this very high energy ball milling. This is a machine that allows you to really make sure you put all the elements into a solid solution. But to do this type of experiments, we had to optimize the milling parameters, and we have done that by running one of these Taguchi compositions, which in fact is a composition which is now being used, but we are not using nickel. currently. So the idea here was to make sure that we could get homogeneous, starting from the elements, not from minerals, that we could get homogeneous compositions and tetrahedrite. So here what you see is that we are trying to see what happens when we change the rotation of the ball mill. And here we're talking about energy, the impact energy provided by the balls to the material. And here we tested for 1 hour with balls of 12 millimeters. And you can see that only at 800 and 1,000 and even at 1,200 rotation per minute, with 1 hour, we still don't get only tetrahedrite, because this peak here, this peak which is at around 28, 29, is another phase called famantinite. So this was 1 hour was clearly not enough. And then we decided, okay, now let's go for 2 hours. And with 2 hours, we can see that for 1,200 rotation per minute, then we only have tetrahedrite. So we were able to select the parameters. The other thing we wanted to make sure was what kind of sphere should we use. And then it turns out that both either 10 millimeters or 12 millimeters are suitable to achieve what we wanted. So in the end, this was what we have chosen as parameters. Then one thing that we tried to do to characterize our material in terms of stability was to use this in situ XRD. So you just do XRD while you're heating your material. And so this was the thermal cycle employed. So we started at room temperature, then we increased quite fast the temperature, we let it stabilize for 2 hours, and then we acquire again another diffraction pattern, and so on. Given that we are thinking of using tetrahedrite for temperatures in the range between 300 and 400, this was the thermal cycle that we have employed. And then if you look here, these are some of the runs we've done with these materials, which were a bit wild because they had too much substitutions. You can see that when you look at the diffraction patterns, which were acquired at different temperatures, so the bottom one is at room temperature, and then the next one is 150, then 300, then 450, and then again, after cooling down, is 25 degrees. And when you look at this, what you see is that most samples are essentially, you see some peaks, but most samples are essentially tetrahedrite. But when we look at the SEM images, what we see is that we have a lot of things going on. There's a lot of decomposition. And the most important aspect that we take from this initial study was that XRD is probably not the best technique. Even if you perform annealing while you're acquiring your XRD patterns, is not the best technique because all the samples, or most samples, had very complex microstructures. And one of the points that was really important and we are investigating now is the fact that most samples, or well, all samples after annealing, they had this type of dark phase. It looked like pores, but we were not completely sure what it was. Now we know what they are. But so this is an important, very important aspect for tetrahedrite, because no matter what the composition is, if you have tetrahedrite after annealing, in our case, so the materials produced by ball milling, you always get this dark phase. So what we have done next was to use scanning transmission electron microscopy. And then here you see that again, you have all these holes, things that look like pores, but we were not totally sure of what they could be. But then I will show you some results. An additional aspect in which TM is certainly the only technique, or one of the few techniques that can provide information, is that when we anneal the samples, we see a very fine decomposition, or a very fine microstructure in the order of the 10 nanometers. And when we look at it, we see that in fact, with EDX in this case, what we have is in fact some sort of regions which are very a little bit more enriched in antimony, and other regions which are a little bit more enriched in copper. And this means that we are probably having the composition to two different types of tetrahedrites at a very, very, very fine scale, which in fact might be interesting for the ZT, but we are still not sure. We are still investigating this. Again, if you go to high resolution TM, you see this contrast difference, which we believe is related to the chemical composition. And this is something we are still trying to understand. So it's between around 10 nanometer scale, you see that there are some regions which have a higher mass and regions which have a lower mass. The structure is exactly the same. And we believe that what we're seeing is possibly the initial stages of a spinodal decomposition. Then the other question was, what is this type of pores? What is this porosity? So at Sintef, we have this DTA TG mass spectrometry instrument. So we just do a DTA and we measure the mass as well by TG, but then we have the possibility to measure the composition of the gases which are being released by the sample. And then what we could conclude from this is that we are losing oxygen, we are losing sulfur from our tetrahedrite. And this means that SO2 is being formed. So you see that we have the mass for the SO2 and SO. After annealing at around 300, so this starts to happen. What we believe, this is a very important result actually, because what we believe is happening is that by ball milling, it's virtually impossible to really remove all oxygen. It's very difficult, especially if you think about the industrial conditions. So we'll always have some oxygen present. And this oxygen will react with sulfur and will form gas in the sample. The most important implication here is not so much the initial fabrication, because of course the amount of oxygen is going to be finite. It's whatever is inside. You form the pores. If they're very nanometric, maybe they might even be interesting from the point of view of scattering phonons, and the ZT might be improved. So that's not really the issue. But the issue is that at above 300 degrees C, it will be very important to make sure that tetrahedrite is not exposed to air. And this has implications at the level of the fabrication of the devices, because it means that they need to be sealed. They cannot be in air, because otherwise you'll have oxygen diffusing in and you'll have the formation of gas, which in the long-term service of the devices will pose problems. Another thing we've done, this is another line of activity related also with the stability and the possibility of the different compositions, is to do density functional theory atomistic calculations in order to try to have some fundamental understanding of the materials. So, so this is again preliminary results, but we can at least have some trends. So when we apply use this to apply these methods to pure tetrahedrite, non-doped, we see that we have quite a large band gap. It's not exactly the value which is published, but it's interesting to compare. So I'm going to show you now when we dope with iron, because this is what we have done, doping with iron and doping with zinc, what we see is that iron indeed has the influence is to close the gap, and this is usually what is best for tetrahedrite, to have a band gap, so semiconducting material, but with a very small band gap. And this is what happens with the presence of iron, and that's why iron is one of the chosen elements by the START project. When we put zinc, then it's completely the opposite. So zinc doesn't really change the band gap that much compared to copper. And then, of course, when you mix both, when you have iron and zinc, then again you have the populated populated region here, saying that we have decreased band gap, which is interesting for the properties of the material in terms of thermoelectric behavior. So now I'm going to show you what we are doing now. So in addition to the characterizations of samples that people send to us, we still have a background activity. So also to combine with the DFT calculations. So we are now working mostly with the third and the fourth campaign, as we tell. That's the name we have internally at Sintef. So in this third campaign, what we're trying to do is for the composition in which the copper and so the transition metals are 12. So we have 10 copper, 1 plus, and 2 coppers, 2 plus. Then in this third campaign, what we are using iron and zinc to replace and then measure thermoelectric properties. In order to also calculate what we are expecting in terms of behavior with simulations. But and this is in fact the composition which has been selected has been around this, with iron and zinc, and around these proportions. So this is something we're trying to do in order to study the material from a fundamental point of view. And then another finding is that if you have excess of copper, usually the ZT is better. So in this case, what we're trying to do is to also study from the fundamental point of view and then validating with results, with experimental results. We are doing this for an excess of 2 atoms. And so again, with a variation between iron and zinc. And then another campaign we are working on is to try to do again a fundamental study and an experimental study in terms of stability for using, friendly elements which are not totally rare. Some of them are already endangered, like cobalt, for instance. But trying to see whether we can, in a more systematic way, study. Some of them are studied and they're found in the literature, but others are not. And so the idea here is really to make a comprehensive study and compare them all in terms of microstructure and ZT. So I'm concluding now. So what we can say is that XRD is in situ XRD is a very nice technique, but in the case of tetrahedrite, the sensitivity is not high enough. So it's very difficult to really make sure that the sample did not decompose. What we can see is that manganese and nickel posed a lot of problems in terms of decomposition. So although in the literature people cite manganese and nickel as having a good thermoelectric behavior, people never really show 2 things. One is that what happens when you cycle a long time, what happens in terms, or many times, in terms of the ZT behavior. And most of all, I've never seen any studies where people show you the samples after a long time annealing or after cycling many times. Because in terms of the stability of the structure, in terms of nanostructure, for instance, or in terms of decomposition, it would be very interesting. And I never really see this published. And this is something we want to change also with START. TM is a good technique if you want to understand what's going on at a very fine scale, and also DFT calculations. And what we see with this DTA combined with mass spectrometry, is that we need to address this problem of oxygen, not so much during fabrication, although that's also an issue, but it might be even beneficial, but more in terms of service. How can we provide or prevent oxygen from not entering tetrahedrite during service? Okay, so I'm done. I don't know if I was able. I tried to combine a little bit results with because our task is characterization. So I need to present some characterization, very specific results as well, and with some of the techniques we can use. But the final message is that at Sintef we have a lot of different tools and a lot of different people with very different competencies. So you already have a contact, which is me. So if you need anything from us, just reach out and contact me. I'm very easy to find, and I'll be happy to help with what I can. Okay, thank you so much for listening, and maybe I can take the questions now. I will go out of mode of this sharing mode.
Yeah, leave the sharing maybe.
No, I will
I
leave the
don't know.
sharing. Sorry, I meant
Yeah,
the full
Eh,
screen.
yeah. The I don't know if there are questions because I don't see questions. Well, thank you first for the presentation, but I don't see questions in the chat. Actually, there were some questions between discussion between Damian and Alvisa, but I don't see questions for you now. Is there anyone that would like to ask? I will try to open again the discussion, the possibility of opening the microphone and camera. I don't know if there's anyone willing to ask, not only to Patricia in case, also for the previous speakers, and we can call them on stage. Leave you some seconds to decide if you want to ask something.
Why is it that people cannot pose the questions live? Is it because they don't click on the
As you've seen,
microphone?
it was possible, so
Uh-huh.
because Jean-Yves made it,
Mhm.
so I don't know what happens with the others. Maybe I think you have to approve the use of microphone. If you haven't approved before, then probably it's a problem. I don't see questions now. I don't even see them typed in the chat. So
Yeah.
I think we have to conclude there are no questions. Maybe.
Mhm.
Maybe can the other speakers come on the stage, and maybe also Filipe. We
Shall I
close.
shall I
Yeah,
share?
yeah. If you want, I think you can. Oh, there is a question now. From Anna. Does iron or zinc change the carrier concentration of tetrahedrite, and how? That's a question.
Well, probably they do. We don't know yet because we have not made that characterization yet. Probably they do. Maybe Philippe can answer this.
Yes, if someone as a reply to this, Filipe, you're there. Maybe you can comment.
I will speak with them.
You are on stage. Yes, I don't see you, but
You don't see
you're on
me?
stage.
Ah, okay. Now you can see me.
Yes. So do you have a reply for this question about?
So do you know, Philippe, how the iron and the zinc will affect the
No,
charge carrier concentration? This is
no.
something we actually need to do now. But
Yeah.
you know, I don't know who was asking this question, but the problem so far is that it has been a bit difficult to stabilize the composition, and you have pores and you have so many different things that we are now at the stage, I believe, where we will start to do some fundamental measurements, because if you have a mess, then what are you measuring? So hopefully very soon we'll start to be able to characterize electrically the samples, and this is something we can also do at Sintef.
Okay. Yeah, see that. Formation energy of zinc is very low. My question is, how did you control the zinc vacancy in
Sorry,
vacancy maybe in tetrahedrite? Maybe it's a typo.
the
Zinc.
vacancy we didn't. So what we have done was we have replaced copper with zinc. But now what we are doing with vacancies, we are well, not so much vacancies. So we didn't study vacancies. We are studying interstitials of copper. So we are now placing copper where it should not be. So, but we are not studying vacancies. Was that the question? I'm not sure if I answered.
Not sure because maybe there was a typo in the question. So because the zinc vacancy, I don't think it's a term.
Zinc vacancy probably, but
It's
Yeah,
today.
vacancy, yes, yes.
yeah,
But
that
it's
was
not
a
zinc
guess.
vacancy. What we've done is we have replaced
Yeah.
copper with zinc. So in the positions where you have a 2+ oxidation state, we replaced some of those coppers with zinc.
Mm-hmm. Yeah. Okay. Any more questions? They seem to come. I don't know. Give you some chances yet to Oh, there's a thank you.
But in any case, if there's fundamental questions, I'm not the person in charge of the DFT calculations. But if you reach me, I mean, if it's something you're interested, and if it might even that be possible to collaborate, if you reach to me, I can put you in contact with the person who is doing all these DFT calculations, so that you can discuss and maybe you can help each other. Who knows?
Right. Good. Okay, I don't see more questions now, so I think that we are more or less at the end of the seminar, of the webinar. What do you think, Filipe? We can summarize something, or?
Yes, I just want to acknowledge the three speakers, Serena, Damian, and Patricia, for the excellent presentations, and also all the attendees for being present and joining us in this webinar. We will continue disseminating our activities through other webinar sessions. So the next one will be in June. I think, Bruno, you already have something ready for that.
Yeah, you should see it
Also.
now on screen.
Yeah.
This is a spoiler. You will see some advertisement in the next months, of course. You will see it in due time. But if you just want to take note and save the date, we plan to have another webinar at the beginning of June. And we're actually moving towards the applications. And now we go to the devices, the thermoelectric devices and the applications themselves. So that will be our 5th webinar, but there will be others, of course. We will have results to report later.
Yeah.
And so please stay tuned. For the moment, save this date. Okay. So I thank as well all the speakers, Patricia, who is still here, and Damian and Serena, that are, I think, still in the meeting, but not on stage. There's Serena.
Yeah.
Thanks again for being here, and we can switch to this view. They're all here, yes. Thanks to all the participants. We were about 40 at a certain point, so not bad. Thank you. See you next time.
Okay. Thank you. Bye.
Thank you very
Thank
much.
you all. See you
Goodbye.
next time.
Bye, everyone.
Bye.
Bye.